By the end of this module, you will be able to define transformer and its working principle, explain construction of transformers, draw phasor diagrams of working of transformer, make an equivalent circuit of transformer, list different types of transformer as per applications, execute tests and maintenance of transformer, and protect transformer from different faults. We have heard the word transformer a lot in daily lives, but what it is? Transformer is a static AC device used to change high voltage low current AC into low voltage high current AC and vice versa without changing the frequency. In brief, it transfers electric power from one circuit to another. It does so without a change of frequency. It accomplishes this by electromagnetic induction, where the two electric circuits are in mutual inductive influence of each other. The operation of transformer is based on the principle of mutual induction, according to which an EMF is induced in a coil when current in the neighboring coil changes. In this section of the module, we will understand the construction of transformer. From the core construction perspective, transformer is of two types, that is, shell type and core type. Click each to know more. Transformer windings are wrapped around the center leg of a laminated core. Here, the representation of shell-type transformer is given. Here, the construction of shell-type transformer is shown. In core-type transformer, windings are wrapped around two sides of a laminated square core. Here, the representation of core-type transformer is given. Here, the construction of core-type transformer is shown. For better understanding of construction, click each of the following concepts and know more. High voltage conductors have smaller cross-section than the low voltage coils. Here is the sectional view of shell-type transformer, and this is the sectional view of core-type transformer. Here is the construction of shell-type transformer using stampings. Here is the construction of core-type transformer using stampings. Click each image to know more. The HV and LV windings are split into number of sections, where HV winding lies between two LV windings. In sandwich coils, leakage can be controlled. This image shows the coil and laminations of core-type transformer. And here are the various types of cores. We take round-shaped core to have minimum winding copper wire. Let us look at the cut section of transformer to understand it more clearly. Click each number to know more. Frame or tank. It protects the transformer core and coils and provides mechanical support to all accessories. core. It provides the magnetic path for the magnetic flux. Windings. These provide the path for electric current. Radiators. It is used to improve the cooling efficiency of transformer. Drain cock. It is used to collect and drain the transformer oil. Rollers. These are used for transportation of transformer. High voltage bushing. It provides support for high voltage terminal with proper insulation. Low voltage bushing. It provides support for low voltage terminal with proper insulation. Conservator. It provides space for the wire during change in temperature. Explosion vent. It is an emergency safety device to protect from high pressure inside the transformer.
Transformer oil. It is stable at high temperatures and has excellent electrical insulating properties.
Buchholz relay. It is a gas-operated relay which gives alarm during overload and trips in case of severe fault inside transformer. Temperature gauge. These are of two types, OTI, that is, oil temperature indicator, and WTI, that is, winding temperature indicator. Breather. It inhales dust and moisture-free air inside the transformer. Let's understand the working of transformer with conservator and breather. Conservator allows extra space for transformer oil to contract and expand due to heat produced because of loading of transformer. While inhaling, breather allows dry air to go inside the transformer, and during exhaling, the air inside the transformer is released in the atmosphere through it. Breather consists of oil pot and silica gel. Oil pot catches dust of air that goes inside during inhaling, and silica gel absorbs moisture of the air. Color of dry silica gel is blue, and after absorbing the moisture, the color of the silica gel becomes pink. Let's look at the working of a transformer. 1. When current in the primary coil changes, being alternating in nature, a changing magnetic field is produced in the core. 2. This changing magnetic field gets associated with the secondary winding through the soft iron core. 3. Hence magnetic flux linked with the secondary coil changes. 4. Which induces EMF in the secondary winding. Depending on the electrical network where the transformer is installed, there are two transformer types, three-phase transformers and single-phase transformers. Let us learn about single-phase transformer. The AC voltage source injects the AC current through the transformer primary winding. The AC current generates the alternating electromagnetic field. The alternating magnetic field gives rise to alternating flux in the iron core of the transformer, thus inducing voltage in the primary as well as secondary windings. Thus, the voltage is induced in the secondary winding with same frequency as voltage of the primary side. The induced voltage value is determined by Faraday's law. ERMS equals to 4.44 into F into N into phi max, where F is frequency hertz, N is number of winding turns, phi is magnetic flux WB. The single-phase transformers can operate as step-up transformer or step-down transformers. In this section of this module, we will learn about the ideal transformers. An ideal transformer is an imaginary transformer which does not have any loss in it. For better understanding, we have divided it in two following parts: terminologies, circuit and phasor diagrams. Click each to learn more. Here are few terms that we need to understand first. Zero leakage flux. Flux is produced by the primary and secondary currents are confined within the core. The windings have no resistance, that is, induced voltage equal applied voltages. The core has infinite permeability. It means the following two conditions. Reluctance of the core is zero. Negligible current is required to establish magnetic flux. Lossless magnetic core, that is, no hysteresis or eddy currents. In an ideal transformer, the leakage flux is considered nil. That means 100% flux passes through the core and links with both the primary and secondary windings of transformer. Although every winding is desired to be purely inductive, but it has some resistance in it which causes voltage drop and I²R loss in it. In such ideal transformer model, the windings are also considered ideal. That means resistance of the winding is zero. Now, if an alternating source voltage V1 is applied in the primary winding of that ideal transformer, there will be a counter self EMF E1 induced in the primary winding, which is purely 180 degrees in phase opposition with supply voltage V1. As the primary winding is purely inductive, that current 90 degrees lags from the supply voltage. This current is called magnetizing current of transformer I mu. This alternating current produces an alternating magnetic flux phi, which is proportional to that current and hence in phase with it. As this flux is also linked with secondary winding through the core of transformer, there will be another EMF E2 induced in the secondary winding. This is mutually induced EMF. As the secondary is placed on the same core where the primary winding is placed, the EMF induced in the secondary winding of transformer E2 is in the phase with primary EMF E1 and in the phase opposition with source voltage V1. Do you know the EMF equation of transformer? Click to view the equation. Here is the EMF equation of transformer. E equals to 4.44 BAFN, where E is induced EMF in volts, B is flux density in WB by M square, A is cross-sectional area of core in M square, F is frequency in hertz, and N is number of turns. In this section of this module, we will understand transformer in different conditions with help of circuit and phasor diagrams.
Drag and drop each voltage bushing on transformer.
A transformer is said to be on no load when its secondary side winding is open circuited. When an AC sinusoidal supply is connected to the primary winding of a transformer, a small current I.O. will flow through the primary coil winding due to the presence of the primary supply voltage. With the secondary side open, that is, when no load is connected to the secondary side, a back EMF along with the primary winding resistance acts to limit the flow of this primary current. Obviously, this no-load primary current I.O. must be sufficient to maintain enough magnetic field to produce the required back EMF. This no-load primary current is made up of the following two components. An in-phase current, IE, which supplies the core losses. A small current, I mu, at 90 degrees to the voltage which sets up the magnetic flux. The phase angle between the secondary current and voltage depends on the nature of the load. If the load is inductive, the transformer will be with lagging power factor. Steps to draw the phasor diagram is as follows.
Take flux phi as reference.
Induced EMF E1 and E2 lags the flux by 90 degrees. The component of the applied voltage to the primary equal and opposite to induced EMF in the primary winding. Current I.O. lags the voltage V1 by 90 degrees. The power factor of the load is lagging. Therefore, current I2 is drawn lagging V2 by an angle phi 2. The resistance and the leakage reactance of the windings result in a voltage drop, and hence secondary terminal voltage V2 is the phasor difference of E2 and voltage drop. V2 equals to E2 minus voltage drop. I2 R2 is in phase with I2 and I2X2 is in quadrature with I2. Current I2 dash is drawn equal and opposite to the current I2. The total current flowing in the primary winding is the phasor sum of I2 dash and I.O.
V1 equals minus E1 plus voltage drop.
I1 R1 is in phase with I1 and I1 XI is in quadrature with I1. The phasor difference between V1 and I1 gives the power factor angle
phi 1
of the primary side of the transformer. The power factor of the secondary side depends upon the type of load connected to the transformer. Steps to draw the phasor diagram at capacitive load.
Take flux phi as reference.
Induces EMF E1 and E2 lags the flux by 90 degrees. The component of the applied voltage to the primary equal and opposite to induced EMF in the primary winding. Current I.O. lags the voltage V1 by 90 degrees. The power factor of the load is leading. Therefore, current I2 is drawn leading E2. The resistance and the leakage reactance of the windings result in a voltage drop, and hence secondary terminal voltage V2 is the phasor difference of E2 and voltage drop. V2 equals to E2 minus voltage drop. I2R2 is in phase with I2 and I2X2 is in quadrature with I2. Current I2 dash is drawn equal and opposite to the current I2. The total current I1 flowing in the primary winding is the phasor sum of I2 dash and I0.
Primary applied voltage V1 is the phasor sum of minus E1 and the voltage drop in the primary winding. V1 equals minus E1 plus voltage drop.
I1R1 is in phase with I1 and I1XI is in quadrature with I1.